Assalamu alaikum. My name is Mobeen Malik, and we were assigned to make a line follower robot in which there were certain modules and some external features that we had to add to make it a complete project. So starting off with the block diagram, this basically represents what are some of the modules and what pins are going to be used on my microcontroller. Battery will we have to monitor the voltage and current of the battery that will be supplied to our circuit, so they are connected to the analog pins of the ATmega 2560. Left encoder, right encoder are the two encoders that will be used to monitor the speed and the rotation of the two wheels. IR sensors are there are 6 IR sensors, namely extreme left, center right, and extreme right. Ultrasonic trigger pin will be declared as an input, as it will detect the ultrasonic waves that it will throw out from the ultrasonic echo pin. RSE, D4, D5, D6 and D7 are the 6 pins for the LCD. PWM right, right motor forward, right motor backward, left motor forward, left motor backward, and PWM left. These 6 pins will be used to control the speed and direction of our motors. MISO, MOSI, SCK and CS are the SPI communication pins that will be connected to the assigned SPI pins in the microcontroller. And the ultrasonic echo pin, as I've told you earlier, will be used to send pulses of ultrasonic waves from the ultrasonic sensor. Starting off with my choice of the microcontroller, I have gone with the ATmega 2560 just because of its number of ports, as it has a larger number of ports available as compared to Arduino Uno or a Nano. The only downside is its size. The PCB that I made is quite bulky, but the good thing is that I was able to restrain it to the size of my actual robot, so that's a plus. Starting off with the modules, this is the module that is used to control the speed and direction of my motors. So the PWM-R and PWM-L are basically the pins where the PWM of left and right motors will be controlled, and they are connected to this pin 9 and this pin number 4. RF, right motor forward, RB, right motor backward, and similarly left motor forward and left motor backward are the pins that will be used to control the direction of the motor. This potentiometer is just used to connect to the LCD, and it will be used to control the contrast of the LCD. This is the connector where the LCD will be connected, and this is the point pin number 3 of the connector, is where the potentiometer is connected. This RS defines where the register select pin is connected on the Arduino. This is the read or write enable pin, and it tells the LCD whether to read or write. This E is the enable pin that will tell the LCD whether to perform a function or not, and I am using my LCD in the 4-bit mode, so the only data pins that I am using are the D4, D5, 6 and 7. The encoders, we were assigned the task to include the encoders in our line follower robot, just to tell us what path our robot has followed and with what speed it is going and whether it is moving left or right. So the encoders are just the optical encoders, and they give out the digital output. So I have connected them to some digital pins and labeled them as E and R, encoder right and encoder left. I have used my encoders to tell me how much to tell me at what angle my robot has rotated whenever it has detected an obstacle. I am rotating my robot to 180 degrees, and when the robot rotates 180 degrees, the tires basically move a specific number of steps, which I have already find out, and I will tell you about that when I'll explain to you the code. IR sensors, the main and the fundamental module of my robot, and these sensors will be used to detect the line, and basically you will be used to follow help the robot follow the line. Simple digital sensors with a comparator IC, and the sensors will be giving out 1 or high whenever they detect a black, and a 0 or low whenever they detect a white. This power connector is nothing but 2 pins that will be used to powering up my whole PCB, where all these modules will be connected. SD card communicates with the microcontroller using the SPI protocol, which is the fastest of the three, the UART and I2C. So the module that I selected was using the communication protocol SPI, so that has to be connected to the specified pins both on the Arduino and on the module itself. So the MISO pin on the SD card module is connected to the MISO pin on the microcontroller, which you can see is labeled right here as MISO and pin number 50. MOSI master out slave in and MISO master in slave out are connected to their respective places, and SCK is basically the clock frequency which will be synchronized amongst both the microcontroller and the SD card module. CS pin is just a digital pin. You can connect it anywhere on the Arduino, and it basically tells whether the SD card is present or not. Current sensor will be used to detect or monitor the current that my battery or power source will be providing to my whole PCB, including the motors and everything. So the current sensor's output is connected to the analog input of the ATmega2560, as the output it gives is some analog value with certain sensitivity. In my case, the sensor I used was ACS712, and the sensitivity it had was about 66 millivolts. Ultrasonic sensor, just a sensor that will be used to detect the obstacle, and whenever the obstacle comes, the robot has to turn 180 degrees and move back to its original position. The start and stop button is just a soft start, which will allow the robot to be on in terms of power, but not on in terms of actual functionality. So whenever I turn on the power of my robot, the robot won't just randomly start following the line. It will stay, and whenever I press the button, only after that it will start following the line. This voltage sensor is nothing but two resistors that I have connected in series, and these two resistors connected in series will actually be connected in parallel to the battery. So the value of the resistor that I've selected is by using the calculations of a simple voltage divider. The battery that I'll be using would be of a 12 volt battery, so I know what my voltage source is, and once the battery is connected to the voltage divider, the voltage across this 37K resistor I know is not more than 5 volts. Now if the battery if the voltage across this resistor is not more than 5 volts, only then I can know and ensure that my microcontroller is safe, because the threshold voltage of what a microcontroller can receive is about 5 volts. So these are the modules that will be used to connect to the microcontroller, and I will explain to you about the PCB. The PCB was just made according to our convenience. I didn't want to include any jumper lines, so I just put the modules where I wanted to, and then connected them to the most convenient pin that was available to me. Suppose I want my IR sensors connector to be at the front of the PCB. So I placed my connector at the front right here, and then connected them to these pins 36, 38, 40, 42 and 44. In that way, I was able to modify my code according to my PCB, as it is a much better approach rather than writing a code and then making the PCB according to your code. You have much more flexibility in modifying your code than you have in modifying your PCB. The ultrasonic sensor I have placed at the front so that the first thing it detects is the obstacle, and does not just go head on into the obstacle and collapses into it. The left and right encoders are at a place that is closest to my tires, where the actual encoders are connected. Motor connections, this connector is at a place which will be the closest to my motor driver. Potentiometer, as you can see, is in a vicinity with this LCD connector, and it will be used to adjust the contrast. SD card module is closest to the actual MISO and MOSI pins that are on the microcontroller, these 51, 50 and 53 pins. The current sensor is closest to the analog pin on my PCB, and I have decided to include the voltage sensor just under the microcontroller. I am not using a market build sensor and which is a bulky module to be contained in a PCB. I'm sorry about that. I had the freedom of including these resistors just below my microcontroller. They are hidden from normal eyes, but they are just there and functioning like a normal voltage, any voltage sensor should. They are lying under the microcontroller. They are hidden and they are connected to this A0 pin, which will basically be the analog input pin of the microcontroller. So this was all about the PCB, and I'll explain to you what the code of the microcontroller is all about. So talking about the explanation of the code, this is where I have declared my pins and ports where on the Arduino, where each and every component will be connected. So from here to here, these are the sensors that will be connected from 36 to 46 pin of the Arduino, and these are the PWM right, forward, reverse, left, forward and reverse, and PWM left of the motor driver, and these will be connected to the pin number 9, 8, 7, 6, 5 and 4 of the microcontroller. This L encoder is the left encoder and R encoder is the right encoder, which will be used as an input pin from the encoders, and these current S and voltage pins are the analog input pins that will be used from the current sensor and the voltage sensor respectively. The echo pin will be used as a digital output that will be sending out pulses of ultrasonic waves, which will be detected by the trigger pin, and this will be used to detect the distance between the robot and the obstacle. Liquidcrystal.h is a header file that contains the functions and commands which will be used for the LCD. sd.h is a header file for the functions of SD card, and spi.h is a header file that will allow us to communicate using the SPI protocol with the SD card module. Unsigned long PT is a variable that initially has a value 0, and this variable will be used in implementing a delay that will not be disrupting our line following or main function. So this delay will be created using the millis command that is built in the Arduino IDE, about which I will explain to you in a bit. Constant unsigned long delay time. Delay time basically is a variable that has the value in milliseconds of what delay I want in my voltage and current values. These are some of the functions that I'll explain to you sequentially. Constant int rs is equal to 23. These are the pins that of LCD that I have declared right down here. In the void setup, I have to tell the Arduino which of the pins are output and which of the pins are the inputs. So pin mode 3 input pull up. This is connected to the interrupt pin of the Arduino, and my soft start push button will be connected right here. Input pull up means that initially this pin will have a high value, and attach interrupt digital pin to interrupt 3. This is where I have declared that pin 3 is going to be used as an interrupt. Start code is the function that it is going to execute, and falling means that it is going to detect the falling edge of basically going to detect the falling edge of the button. These all the sensors, IR sensors, are declared as an input, and the motor pins are declared as outputs. Current and voltage sensor again are going to be declared as analog inputs, so I don't have to mention analog with them. The ultrasonic trigger and this line actually is not necessary right here. The trigger pin and is declared as an output, and echo pin is declared as an input. LCD begins 16x2 means that the 16x2 LCD is going to be used, and it has about 16 columns and 2 rows. So in the main loop there is a variable which is of unsigned long data type, and it is storing the value from the millis function. Now what millis function does is, millis is a built-in function that whenever you start executing your command, whenever your Arduino is started, millis returns a value from 0 to 4.9 billion in about in increments of about 1 millisecond. After 1 millisecond, the value increments from 0 to 1 and so on. So for a millis function to run completely, it takes about 45 days for it to completely return all of its values. So anytime in the code, the value of millis is stored in CT. Now if button modulus 2 is equal to 0, button is a variable that has a value 3. So whenever I press the soft push button, it will go into its respective ISR, which is basically the interrupt service routine or any function, and increments in the value. Now if button goes from 3 to 4, then in the main function this mainline command starts to execute. Now what this mainline does is, it is basically my main logic on the basis of which my line follower will start working. If digital read extreme right is high and digital read extreme left is low, which means that right sensor is on and left sensor is off, then it has to follow or go right. Else it has to go left. And if none of the these condition is true, there is an other function which will detect the other 4 sensors, and on the basis of their values it will tell the robot what to do. This is the line follower function, and these are the functions that will tell the robot where to go. This forward function will turn the motor right motor forward and left motor forward high, and the PWM with which they are going is 150. Same goes with the left. In the left function, the right motor forward is high, and now we know that to turn your robot right, the left motor should be working, and for turning your robot to the left, your right motor should be working. For braking, all the motors are turned off. Now after the main line has executed once, we have a check that if CT minus PT is greater than or equal to the delay time, that means if this variable or the millis value is difference of the millis value with our PT variable is greater than our desired delay, then the voltage detection and current detection function will be called. Otherwise, our main function will keep on calling this main line function. In the voltage and current detection, there is a variable with the name of value, and it will take the value as analog read from the current pin, and it will multiply it by the maximum value the sensor can give out, that is about 5000 millivolts, and we will divide by it the resolution of our ADC. Now the ADC in the 2560 is of about 10 bits, and once these 10 bits are done, then our value is basically divided into these 10 bits, and then it is again divided by the sensitivity our sensor has. Same is the case with the voltage detection. We have multiplied it by the 5, which is the maximum value that we can give to our ADC pin, and divided by its resolution and dividing by its sensitivity. Now this value is achieved by the value of our resistors that we have used in our voltage detection system or the voltage sensor. After executing this voltage and current function, it will go, the value of PT is redeclared equal to the CT. Now whatever the value of CT was at that time, it is stored in PT now, and the delay function is kept on checking again and again. Now the use case of this condition is that whenever my robot is actually following its line, this current and voltage detection system will not interrupt in the actual line following function. And the delay is necessary to actually show some stable values on the LCD. After this voltage and current detection system, current detection functions are called, there is another function which is named as reversal. Now what reversal does is, it will store the value which this ultrasonic distance function gives into a variable x. Ultrasonic distance function has a variable name with the name of duration, and another variable with the name of distance. This digital write and these functions, basically what they do is they will turn off the trigger pin, then turn it on for about 10 microseconds, and then again turn it off for about 2 microseconds. What this basically does is it generates pulses of ultrasonic waves that are thrown towards the obstacle, and then they echo back towards the ultrasonic sensor, which are detected by this echo pin. Now the duration is detected using this pulse in command. The time taken by the waves to go and come back is stored in this duration, and that time is multiplied by the speed of sound. As we know, the ultrasonic waves travel with the speed of sound, and divided by 2, because the time taken by a wave, it travels basically 2 distances, one in going towards the obstacle and then echoing back from it. So we have to divide it by 2. This is the distance variable which will be returned to this reversal function. Now if the distance is less than 10, that means that the obstacle is less than 10 centimeters to my robot. What it will do, if the distance is less than 10, that means that the obstacle is 10 centimeters away from my robot, it will start moving right. This right function will be called, and it will be called for whenever the steps are less than or equal to 32. Now how do I know that to rotate my robot 180 degrees, the robot has to move 32 steps? When my robot wasn't even assembled, what I did was I patched up my encoders and my Arduino, and using the serial monitor of my Arduino from right here, I manually rotated my robot 180 degrees. Now when the robot rotated 180 degrees, it gave me a specific value of the steps, and now that value came out to be 31, 32, sometimes 30. So the average value to turn my robot into to turn my robot 180 degrees, I had to move it about 32 steps. So after it has rotated 180 degrees or it has moved 32 steps, there is a delay of 500 milliseconds, and the main function keeps on calling again and again. So this sets my robot into a continuous loop that will allow it to follow the line as well as detect an object, and whenever an object comes, it will rotate 180 degrees and go back to its starting position. This demonstration is also shown in the video I will be attaching at the end of this presentation, in which you can see that whenever I place my hands in front of my robot, the robot turns 180 degrees and it keeps on following the path. Now this steps function basically returns the value of the steps or the rotations my tire has moved, and this SD card function, which will be called which is called in the mainline function, what it does is it opens up a file with the name of our roll numbers and writes the value of voltage and current in that file and then closes that file. Whenever mainline function is called, this value is these values of the current and voltage are being stored in that file, and that file was also shown in the demonstration of our project while in the university. So this is the only functionality that we are achieving from the SD card. So this basically concludes what my code is doing with my line follower robot, and now I will show you the demonstration of how the robot was actually working.